Hello. In this video, we will go over vector functions. What is a vector function? A vector function is a function with a scalar input and a vector output. The format for the vector output depends upon the number of dimensions. So for example, in 2 dimensions, the format for the vector output would be a vector with f of t in the x component and g of t in the y component. This can also be written in the alternative format using unit vectors. In 3 dimensions, right, so this is 2 dimensions. In 3 dimensions, we would just add an additional component. And again, it can be written in the alternative unit vector form. Okay, so the key to understanding vector functions is the fact that a vector function consists of individual functions in each component, right? So the fact that we have an individual function here and an individual function here, and that is the way that we go through and define a vector function is extremely important. It's the critical piece of information to understand how vector functions work. What this allows us to do is it allows us to take operations that we've previously performed on single functions and apply them to vector functions. Okay, and the way in which you do that is if you're applying an operation on a vector function, you just end up applying it on the individual functions. So let me show you an example of that, right? So for example, let's do an example. We've got given r of t equals t squared comma 1 over t. We can go through and we can plug in numbers into the vector function, just like in the past we've plugged in numbers into individual functions. And when we do that, what we're going to do is we're going to plug in the number into each of the individual functions, right? So if you plug in r of 1, so you're going to plug 1 into the first function, just like we would normally have previously plugged 1 into f of t. And so we would get 1 squared, and then we would plug 1 into g of t, just like we would normally have in the past, and that would allow us to get 1 comma 1. And if we wanted to plug in 2, we would just plug 2 into the individual function. So you just plug 2 in to t squared, and so that would get us 4, and then you plug 2 into 1 over t, and that gets us 1/2. Okay, and then we could plug in 3, and we just plug 3 into the individual function. So you plug 3 into t squared, and that gets you 9. You plug 3 into 1 over t, and that gets us 1/3. Okay. The same thing is going to be true if we go through and extend our ideas for regular functions to vector functions. So the first idea that you deal with when you're introducing a regular function is the idea of a domain. So how would we go through and calculate the domain of a vector function? So, well, first of all, the domain of a vector function has a similar definition to the domain of a regular function. It's the set of all inputs, right? It's the set of all t, right? Assuming you've given r of t as your vector function. It's the set of all t such that R of t produces a finite output. Now that's the same definition as for an individual function. So we just have taken our definition for individual functions and we just have extended it and applied it to R of t. Now, in terms of how you go through and find the domain of a vector function, the way that you do that is you find the domain of the individual component functions and then find the intersections of those. Okay, so let's see an example of that. Suppose you're asked to go through and find the domain for R of t equals t squared 1 over t square root t plus 3. So just like on the previous example, when we wanted to plug in a number, we went through and we plugged it into each of the individual components. If we're asked to go through and find the domain, we want to find the domain of each of the individual components. Okay, so we can do the domain for t squared. Okay, and the domain for t squared is all real numbers. And you could find the domain for 1 over t, and that's going to be all real numbers except for 0. And we could find the domain for the square root of t plus 3, and that would be all real numbers greater than or equal to -3. And so the domain for the vector function itself, we need to combine these in some way, and the way that you combine them is you combine them by finding the intersection. So the intersection of these three, so it has to have, all of these have to end up being true. And so to get a true statement for all three, we'd have all real numbers except 0 and greater than or equal to -3. And the all real numbers is implied. Okay, and that's how you go through and find the domain of a vector function. It's by finding the domain of the individual component functions. Okay, let's move on to the next. All right, so how about limits, right? So the next thing that you do after you have functions and you plug numbers into them and you find domains is you have limits. All right, so how do you find the limit of a vector function given a vector function? If we want to find the limit as t approaches a of r of t, that equals the limit as t approaches a of f of t and the limit as t approaches a of g of t. So as you can see, if we want to go through and find the limit of a vector function, the way that we do it is by finding the limit of the individual component functions. Okay, so that is consistent throughout. And that is the key to understanding vector functions, is that if you want to do something to a vector function, you end up doing it to the individual component functions. All right, so, oh, and of course, this could also be extended to 3 dimensions. So I'm not going to write it again, but you can go through and write that out. let's look at some examples. Let's say we have the limit as t approaches 0, and our vector function is e to the 3t, comma, sine t over t, comma, natural log of t plus 1. Okay, so if we want to find the limit of a vector function, the way that we do that is by taking the limit of the components. So effectively, the limit just kind of distributes into the vector function. And then we have to break off the cobwebs to recall how to go through and calculate limits. The way that you calculate a limit is if the limit value is in the domain, then you can just plug in. So we're going to get e to the 3 times 0 here. Here, if you go try to plug in 0, you get 0 over 0. So 0 is not in the domain. But the fact that we get 0 over 0 will hopefully ring some bells that you could use L'Hopital's rule. So L'Hopital's rule tells us that we can differentiate the top and bottom, and the limit value will not change. So the derivative of sine gives us cosine, and the derivative of t is 1. And then here, 0 is in the domain, so we can plug in. Okay. And then we get e to the 0. We're going to get cosine of 0, and then natural log of 1, which if we simplify is 1, 1, 0. Okay. And so there's an example of how to go through and find the limit of a vector function. Let's do one more of those. So this time we're finding the limit for infinity. And as you will see, that does not change anything. Okay, so we still end up taking the limit and applying it to each of the individual component functions. Okay, in order to calculate the first limit here, we can recognize that we have a polynomial over a polynomial, and when you're simplifying with polynomials, you can go through and calculate the limit by just taking the leading terms. The leading terms will define the behavior for the entire fraction, right? The leading term from the numerator and the leading term from the denominator. And then here we could recognize, oh, we've got infinity over infinity, that it, we could go through and use L'Hopital's rule again for that. So if we differentiate the top, we get one over t, and then the derivative of the bottom, e to the t. And then at this point, you can go through and you could cancel these t squareds, and the limit as t goes to infinity of 3 is going to be 3. And here the limit as t goes to infinity, you could rewrite this. This is 1 over t e to the t. As t goes to infinity, you're going to get infinity times infinity down here in the denominator, and infinity in the denominator. 1 over infinity is going to give us 0, approach 0. Okay, and so there's an example where you're calculating the limit as infinity, and we can see that again, nothing changes. Okay, so next, let's look at vectors geometrically, vector functions. So how do vector functions work geometrically? So the vector function r of t equals f of t comma g of t produces vectors that terminate at the points of the corresponding parametric equation. Let's see that in action. Okay, so well, just in just a second. So that's basically what vector functions do geometrically, right? So what a vector function is going to end up doing is it's going to produce vectors, and if you go through and you graph those vectors with the initial point at the origin, then the vectors are going to end up terminating at points that match with a corresponding parametric equation, and that relationship is going to end up being the key to understanding vector functions geometrically, is the relationship with the corresponding parametric equation. But first, to just go through and kind of prove this to ourselves, let's go through and pick an example and draw some pictures. Okay, so let's say we have r of t. We'll pick something simple here. T squared comma t. Okay, let's draw ourselves a coordinate axis. All right, and then over here off to the side, what we're going to do is we're going to look at the corresponding parametric equation. Now, how do you find the corresponding parametric equation? Well, this is the x component of the vector, and this is the y component of the vector function. So what we can do is we can go through and set x equal to this component and y equal to that component, and we'll get a parametric equation. So you get x equals t squared and y equals t. Okay, and again, let's say that we want to graph this too, so you just kind of can see the relationship. Oh, that's upside down. There we go. Okay, so let's go ahead and to graph this, let's go ahead and plug in some inputs and generate some outputs, and then we can graph those inputs and outputs together. Okay, so if we've got r of 0, we'd end up getting 0 squared comma 0. If we had r of 1, we would get 1 comma 1. If we had r of 2, we would get 4 comma 2. Okay, and now let's do the same thing over here, right? So we're going to have t. So we'll have x and y, right? So if t is 0, okay, then we're going to take 0, plug it in here, and we're going to get 0. We're going to take 0, plug it in here, and we're going to get 0. If t is 1, we'd plug that in here, and we'd get 1. Plug that in here, and we'd get 1. And if t is 2, we'd plug that in here. 2 squared is 4. And t is going to be 2. Okay, and so you can see the points that we end up getting are 0, 0, 1, 0, and 4, 2. All right, so this picture here, the vector 0, 0 is the 0 vector, so that's just that we can represent that just as a point. The vector 1, 1 looks like that. And then we have the vector 4, 2. Okay, and if you want, you could go through and say, this is t equals 1, this is t equals 2. Since the t is not visible on our graph, you can just label it. All right, so, and then t equals 0 is this guy at the origin. All right, now if we were going to go through and just plot points from the parametric equation, what points would we get? We would get the point 0, 0, and we'd get the point 1, 1, and we'd get the point 4, 2. Okay, and then this is t equals 0, t equals 1, t equals 2, right? And so we can see that geometrically, a vector function, it produces vectors that terminate at the points, right? Terminate at the points of the corresponding parametric equation, right? And you could see that that happens organically, right? So if you're going to go through and plug inputs into the vector function, you end up plugging them into the individual components. And if you then take the individual components and use them to define the parametric equation, then when you plug in values, you're going to end up plugging them into the individual components. So you're doing the exact same thing, except one produces vectors and the other one produces points. Okay. So with that in mind, this method here, where you end up graphing the vectors, it's a cumbersome method. And so what we're going to do is we're going to define the graph of a vector function to be just the termination points of the vectors. As a result, because of the fact that we have defined that, we place that restriction on vector functions that we don't end up graphing the vectors, we just end up graphing. So if you're asked to go through and graph this, you're actually not going to draw this picture. You're just going to draw where the termination points are. You're going to draw this point because that's the termination point for 0, 0. You're going to put this point because that's the termination point for 1, 1. You're going to put this point because that's the termination for 4, 2. Because of the fact that we're going to place that restriction on what we consider to be the graph of a vector function, as a result, the graph of a vector function is equivalent to the graph of the corresponding parametric equation. So what that enables us to do is, if we're asked to go through and graph a vector function, what we can do instead is go through and graph the equivalent parametric equation. So let's go through and do that next. And we can graph the example that we were just doing previously. Okay, so the first thing that we're going to do to graph this vector function is we're going to find the corresponding parametric equation. the way that you do that is you set x equal to the x component, y equal to the y component. All right, so you want to think of this in steps. This is the first step, and then the second step to go through and graph the equivalent parametric equation. What we need to do is we need to go through and do what's called eliminating the parameter. If this is unfamiliar to you, then you may want to go and watch a video on parametric equations, and in particular graphing parametric equations. So the way in which you do that is you take the y equals t, since x equals t squared and t equals y, we can just substitute y in place of the t, and we'll end up with x equals x equals y squared. And then we can go through and graph that. Okay, hold on. Okay, so the graph x equals y squared. You can go through and you could find this by plotting points if you're not familiar with how to graph x equals y squared by just taking y equals x squared and reflecting it across the line y equals x. Instead, what you can do is you can plot points. So the way in which you plot points in a case like this is that the independent variable is the y here. So you plug in for the y and then find x. So if you plug in y equals 0, you'll end up getting x equals 0. If you plug in y equals 1, right, we'll end up with x equals 1. If you plug in y equals 2, you'll end up with x equals 4. You could also plug in y equals -1, and you'll end up with x equals 1, and then y equals -2, which gets you 4. And we end up with that. That's our graph. And then when you graph a parametric equation, you put arrows on it to denote the direction of increasing t. Okay, and so this is the graph of our vector function. This is what the vector function looks like. Now, if you went through and plugged in t values, keep in mind what would happen is you'd get vectors that terminate at all of these points. Okay, so the vector function does still produce vectors. It's just that when we graph it, we don't draw the vectors. We just draw the termination points. And again, since the termination points are going to be the same as the points for the parametric equation, instead, we just focus on graphing the parametric equation. So it just takes this initial step where we start with a vector function, we translate it into the equivalent parametric equation, and then we graph the parametric equation. Why do that? Just for clarity, because I did not really make this clear, and that is that we already know how to graph parametric equations, right? That was covered in a previous section. And so what you can do is you can go through and take something that you know, which is how to graph a parametric equation, and use it to graph something that you didn't know, which is a vector function. Okay, so that's the basic idea for why we would want to turn vector functions into parametric equations. It's because we already know how to graph parametric equations by using this eliminate the parameter method. Okay, and again, if this is something that you're unfamiliar with, then what you need to do is you need to go and watch a video on parametric equations, and in particular, graphing parametric equations, because this technique is fairly straightforward. Okay, so let's do some more examples. Let's say that we're asked to go through and graph r of t equals sine t comma cosine t. Then step 1, you're going to translate into the equivalent parametric form. Step 2, we need to eliminate the parameter. Okay. The way in which you eliminate the parameter when you have sine and cosine together is you end up you use the identity. So this is another classic technique that would be covered in a parametric equation video. So we start off with the trig identity, sine squared plus cosine squared equals 1. And then since sine equals t, that means we can pop in x in place of sine t, and we'll end up with x squared. And since y equals cosine t, we can put y in place of the cosine t, and we'll get y squared. And then if we're asked to go through and graph that, how do we graph x squared plus y squared equals 1? Well, that's just the graph. That's just a circle, right? And so we can go through and graph that. So it's a circle, in particular of radius 1. Okay, and then whenever you graph a parametric equation, you have to find the directionality of it for increasing t. And the way that you can find that is by plugging in points. And again, that's typically the way that's done. So if you plug in t equals 0 into this, you're going to get x equals 0 and y equals 1. So this point here is t equals 0. And then if we plug in t equals pi over 2, you're going to get 1, 0. So here would be t equals pi over 2. And from this, we can infer that the motion is clockwise. Okay. Let's do a third example. Okay, so first we want to go through and translate this into the parametric. And if you look at that, right, hopefully that looks familiar. That's our parametric form of a line. Because of that fact, you don't need to go through and translate this and try to eliminate the t. That would just put it into the synthetic form, right? We can go through and figure out how to graph up the parametric form of a line just by recalling what we know about that form, right? And that is that the first piece of this is the point, and the second that's next to the t is the direction vector. Okay, and so to go through and graph that, we want to go to the point 1, 1, 2. That's the starting point for our line. So we've got 1, 1, 2. So that's going to be the point right about there. And then the direction vector here, that's going to give us the direction where we have more points. So it's saying that direction vector is going to have an x component of 1. So if we went 1 from there, if we went 1 unit in the x direction, maybe draw a little squiggly line to denote that. And then we went 2 units in the y. Let's say that's 2 units. And those are roughly the same. And then we have 1 unit in the z. So that's 1 unit. Okay, so this is a point that's on the line. This is a point that's on the line. If you just draw the line that goes through the 2 points, and we can use a different color for that, you'll end up getting a picture of the line. Okay, and that's how you can go through and graph a line using a vector function that ends up producing a line. And let's do another example. Okay, so this is a classic example of that you encounter when you go through and you graph vector functions. So our parametric equations would be x equals cosine t, y equals sine t, and z equals t. So the thing is, the eliminate the parameter method that is, again, is covered in a parametric equation video. It only works in 2 dimensions. In 3 dimensions, it's much iffier. So yes, it would have worked on the last example where we had a line, but it would not work on this example. There's no way that you could go through and eliminate the parameter for all 3 of these at the same time to get a single equation that has x, y, and z. When that happens, what you want to do is you want to pick 2 of the equations, eliminate the parameter, and then the result of that is going to give you a restriction on where the graph is going to live. Where the graph is going to of the vector function is going to be when you go through and graph it. All right, so I'll show you what I mean by that in a second. All right, so if we take these 2, we've got the sine and cosine. So we already know how to handle sines and cosines together. So if you go through and you do sine squared t plus cosine squared t equals 1, then we're going to get y squared plus x squared equals 1. Or you could rewrite this as x squared plus y squared equals 1. All right, and that forms a circle. However, because we're talking about 3 dimensions, this is going to give us a restriction on the relationship between x and y. So the x and y, this has to be true for all x and all y for the parametric equation. In other words, the points that are on the curve need to lie on this. So how could you represent that? The way that you could represent the fact that points for the vector function have to lie on this, have this relationship, have to lie on this curve, is you can go through and you can actually graph a cylinder. All right, since x squared plus y squared has to be true for all points that satisfy the vector function, what we can do is we can go through and graph a cylinder. So here's our cylinder. Okay. And again, why are we doing that? Let's just recap one more time. So we went through and we picked 2 of the variables. We eliminated the parameter. That got us a relationship between those 2. That relationship has to be true for all of the points for the vector function. Now, what is that relationship? It's represented by this circle and the cylinder effectively, because the points for our curve may not all have z equals 0, which is where the circle is. By going through and extending the cylinder upward, we've covered all possible z values having this relationship. All right, so long story short, the graph of the vector function has to lie on this cylinder. Okay, so once you've done that, figuring out what part of this cylinder our curve is going to lie on, the easiest way to do it is to go through and use test points. Okay, so when you've gone through and you've done something like this where you've eliminated, the parameter, and you've got a relationship between 2 of the variables, and you've drawn a curve, from there you could go through and just plot some points. Now, plotting points from the beginning is much iffier. I mean, you could say, well, hey, why don't I just plot points here? Why don't I just plot points here? Why don't I just plot points on all of these right from the start? It's because that's much more time-consuming method. It takes forever, right? It's hard to tell just from plotting a few points what the resulting object is going to look like. However, in this case, it's really the only method moving forward. Once you've eliminated the parameter, I mean, you could go through and you could try and pick z and y and eliminate the parameter again, but in the end, usually that's not helpful to do that. Usually, once you've eliminated the parameter with just 2 of the variables, from there, you want to just go ahead and plot points. Okay, so what happens if we go ahead and plot points? So if you plug in t equals 0, you're going to get x equals 1, y equals 0, and z equals 0. So you're going to get this point here. And you can label it, this is t equals 0. Okay, if we go through and plug in t equals pi over 2, right? T equals pi over 2, we're going to get 0, 1, pi over 2. Right, so this is not going to be vertically to scale, but I'm going to go ahead and say that's this point here, right? This point does correspond to x is 0 and y is 1 and z is some positive value. We're going to go ahead and say that's the point for t equals pi over 2, even though vertically it's not to scale, right? If this is 1 unit, pi over 2 is more than that. But just for simplicity's sake and to make it fit in the picture, we're going to do that. All right, and then if you go ahead and plug in t equals pi, what happens then? All right, if you do t equals pi, now x is going to be -1, y is going to be 0, and z is going to be pi. All right, so where's that going to be? So x is -1, that's back here. And where x is -1 and y is 0, that's back here. And then if you go up pi, so it's going to be 2 of these. So if you go up 1, 2, we'll say it's right about there. Okay, so that's going to be the point t equals pi. Okay, and so you can see we started here and then we went to here. So we went around the edge of our cylinder, which is what we said had to happen. All the points need to lie on that cylinder. We went around the edge of the cylinder, moving upward, and then we went around further and we moved upward some more. Let's do one more. So if you do t equals 3 pi over 2, then x is going to go back to being 0. Then y will be -1 and z will be 3 pi over 4. So where would that be? That would be back here, and then 3 pi over 4. It's going to be 3 of these. So we'll have 1, 2, 3. I don't know. We'll say maybe it's here. All right, so this is t equals 3 pi over 2. And so at this point, can you tell what's happening? So if you can go ahead and just actually draw curves that connect these points, because these points are happening in a row. So you're starting here and then you're going here. So if you were to draw a curve, it would look like that. And then from here over to here, if you draw a curve, it would look like that. And then from here to here, if you draw a curve, it would look something like that. And if we kept going, all right, we would get the next one would be something like that, and then something like that, and then like that, and so on. Okay, and can you see what's happening? So we're spiraling up this cylinder, all right, in this shape. So this shape is called a helix. Okay, so you see helixes occasionally in real world applications such as DNA. And so that's how you go through and graph this. It's a classic example. Regularly, when you go through and do a graphing vector functions section, usually at some point you graph a helix because it's kind of neat. It's a neat result. Okay, let's do one more. And just to change things up, we'll use the unit vector form. All right, so first step, we want to translate this to the parametric. So you get x equals 1, y equals sine t, z equals cosine t. All right, so this is a good example because there's, when you see something like x equals 1, that's actually very, very helpful information for going through and graphing the resulting object. All right, so what does that tell us? That tells us that the curve itself needs to lie, it needs to have x equals 1 as the x component, but it tells us that the curve has to lie on the plane x equals 1. All right, so it tells us even more than that. So it's not just that the x coordinate has to be 1, but that implies that the whole thing lies on the plane x equals 1. So what you could do is you can go to x equals 1 and you could just even draw a plane there and say, you know what, my curve is going to be on this plane. All right, so I'm just drawing a plane here at x equals 1. My object is going to lie on this plane. All right, to figure out what part of the plane you're going to end up with, you can go through and eliminate the parameter for the other two, right? And again, we have this sine squared plus cosine squared. equals 1. We get y squared plus z squared equals 1. And so that's a circle of radius 1. And so you just want to draw a circle of radius 1 in y and z. And so that's going to be, we'll say that's 1 unit. So say 1 unit is right about there. Then we'll go up 1 unit for z, 1 unit, 1 unit. So you get this circle. Like that. And then you can go through and use test points to figure out the orientation. Plug in t equals 0. T equals 0, you're going to get 1 for z and 0 for y. So that's right here. That's t equals 0. And then if you plug in t equals pi over 2, you're going to get this point here. That's t equals pi over 2. And so we can see that it's clockwise. I think that's the same example from earlier, but that's fine. Okay, and that's it. And it occurs to me to add one more detail, just going back to this previous graph. All right, so one of the things that is important to know about vector functions that have one input like this, so we'll get into vector functions later on in the semester that have 2 inputs, but if you have a single input for your vector function, then the object that is produced is always a line or a curve, right? So you should never have a surface. So if you go through and you're doing this problem and you had the entire cylinder as the graph of R of t, that cannot possibly be correct. Okay, so you should get a line or a curve whenever you're going through and graphing vector functions that have just a single independent variable like this, a single independent t. Okay, so that concludes the video on vector functions. Thank you for watching, and I'll see you next time.